here basically this s gets replaced with theta, v replaced with angular velocity, and acceleration replaced with angular acceleration, and these three equations become somewhat like this. So these things we already discussed. So basically what happens is, so one thing is x equals to r theta, and so dx by dt, that is equals to r d theta by dt, which implies v is equals to r omega. This was one formula. So v is the velocity, v is the velocity of the particle on the path. Okay, so v is the velocity on the path. Okay, and omega is the angle rotated per unit time. Okay, no, omega is the velocity, angular velocity. That means d theta by dt, rate of change of the angular distance. So rate of change of this becomes omega. R is nothing but the radius. Right? So since rate of change of distance is the velocity, I mean displacement is the velocity, but here the thing is velocity will always be changing in circular motion. Since it's not a fixed direction always. Okay, so at every point the velocity is getting changed, so there has to be an acceleration here. So change in velocity is called acceleration. So we always deal with an acceleration. So the tangential acceleration here is equals to r alpha. Again, if you differentiate this, so dv by dt is your acceleration on the path. Okay, so this is the acceleration on the path. This was velocity on the path is equals to r alpha. This is called the angular acceleration. Fine. So this was just formula. So formula also basically this was same formula related to the previous only, and there was one new relation was there in terms of tangential distance and the tangential and the angular distance, tangential velocity and the angular velocity, tangential acceleration and the angular acceleration. So when we say that there is a tangential acceleration, we actually mean that, yeah, this is if you can say that it is the length of the arc only. See, this is the distance, no, distance traveled by on the path of the circle is the arc, right? So this is the arc, let's say. So this is not a straight line, so this is an arc, and if this arc makes an angle theta here, so the relation goes something like this: x equals to r, and from this only all other relation comes. This comes and this. So basically, what we are dealing here with is ever changing velocity. So velocity always changes, even though the value of the velocity may be same. Let's say the velocity here is 5 meter per second. Let's say the velocity here is again 5 meter per second, but the thing is the velocity will be changing because the direction is changing right now. So the velocity is a vector quantity which has both magnitude and direction. So when the direction is changing, we say that the overall velocity is changing, since velocity is a vector quantity. So since there is always change in velocity, so there has to be an acceleration in circular. Okay, so there has to be a force in the circular. For simplicity, we will study uniform motion, uniform circular motion now. And what we'll do is we will solve a few questions. When you get somewhat confidence on those things, then we will move on to non-uniform circular motion, where the speed will be changing. So this uniform circular motion means basically constant speed on the path on circular. So the speed is constant, velocity is always changing. We already know. So the previous example what I gave you, 5 meter per second, this is the speed, right? So this is speed. The speed is same, no? Velocity is changing because the direction is changing, but speed is same. The value is still 5 meter per second. So this kind of a circular motion is called the uniform circular motion. Okay, so the acceleration here is always towards the center, and as I told you in the previous class, a is equals to v square by r, or the acceleration, the centripetal acceleration. I'll just put c here for centripetal acceleration. This is also equals to omega square r. This one I had told you in the previous class. V square by r or omega square r, both you can write. Right, no, v is equals to r omega. No, if you put this v is equals to r omega here, it becomes this. I'll tell you one more thing. Like overall, the total acceleration, no, total acceleration will be what in a circular motion? So the total acceleration will be, no, acceleration will always be there. So let's say a body is moving in circular motion. Okay, so every time it is having a velocity. So this velocity v itself can change, no? Let's say the velocity is v1 here, let's say the velocity is v2 here, let's say the velocity is v3 here. So the velocity itself is changing, and we know that there has to be a central acceleration every time. So the velocity this will be a central acceleration, and there will be a tangential acceleration also. So the total acceleration circular motion is given by the tangential acceleration plus the centripetal acceleration. So this centripetal acceleration is towards the center, and this is, so basically this the total acceleration in a circular motion is basically sum of two accelerations. So one acceleration will be at the tangential acceleration, and there will be a centripetal acceleration right now towards the center. So basically the overall acceleration, the acceleration total, the total acceleration, which is also given by the angular acceleration alpha. The total acceleration is angular acceleration alpha, which is given by the sum of these two vectors. So it may be somewhere in the middle. So for the convenience, what we will study now is we will study uniform circular motion, whereas there is no tangential acceleration. The angular acceleration is equals to a tangential plus a centripetal. So this will be 0, and there will be a centripetal acceleration only. So the overall acceleration, that means total acceleration in a uniform circular motion, will be equals to the centripetal acceleration only. No, tangential acceleration will not be always 0. This is the case where tangential acceleration is 0. Tangential acceleration basically means acceleration on the path of the motion. So there is no change in speed, right? So at any moment for one particular instant there is no change in speed. So for that particular moment you can assume that there is no change in velocity for just a moment. With the same speed it's moving, no? So there is no tangential acceleration at that time. So the total acceleration is only towards the center. That is equals to v square by r or omega square r, whatever. But in this case, this is the general case what I told you. General case, what can happen is the velocity can change in the path also. So some car is moving with 50 meter per second, 60 meter per second, 70 meter per second. It's going on speeding. So there is an acceleration on the road also, and there is an acceleration due to circular motion also. So the circular motion acceleration, basically the centripetal acceleration is towards the center, and one more acceleration is on the path of the body itself. Right? No, the car itself is speeding. So this see, you can see that the velocity is changing. No, the magnitude of the velocity is changing. So there will be an acceleration on the path also, that is called the tangential acceleration, and there will be always acceleration. The centripetal acceleration will always be for a circular motion. So the total acceleration will be somewhere in the middle. So just have this in mind, this thing, but this will come later again. Okay, for difficult problems they may include this tangential acceleration also. So let's assume now that we are studying only uniform circular motion, and we'll just see some questions. So one thing we have to understand is there has to be a force towards the center, then only a body can move in a circular motion. We saw in the previous class, no, the example of a stone attached to a string, the example of the earth moving around the sun, right? So there has to be a central force acting for a body to move. For a body to move inside a circle, there has to be a central force acting. So let's say what is happening is, let's say you are moving in a straight line. Okay, so let's say a scooter is moving in a straight line, it's going straight line. Now you suddenly want to take a turn. Okay, so this turn, if let's say this is a road, okay, this is a turn. So you want to just turn your path. So you're moving like this and you just wanted to turn now. So this is not a complete circle, but still this is a part of a circular motion. You're getting my point, no? So this particular curve may be a part of a circle. This particular curve may be a part of a small circle. So when you are taking a turn, there has to be a force towards the center. You just imagine a situation where you are trying to drive a bicycle on a road, a slippery road. Okay, you can somehow manage it driving straight, right? No, but let's say you want to take a turn. That will be very difficult for you to take a turn on a slippery road. You can somehow manage to ride it slowly straight, but if you want to take a turn you will slip, right? No, because there was no sufficient force for you to provide a force towards the center of the circle. So basically what happens is, the cycle, the frictional force is the force. In this case, in this example, the frictional force is the force which actually gives lets you turn in a circle. Yeah, it was rainy or it was slippery, so the friction force was reduced. So the necessary friction force was not there to give a force towards the center. That's why you were not able to turn. Understood, no? So there is a force needed towards the center of the circle to get into a circular motion. Now let's say we'll just see an example. Let's say a simple question number 4. Just see the question number 4. See, one tangential see, it's speeding, it is moving with a constant speed, no? So the horizontal force is not the tangential force, it's the force towards the center of the circle. See, one thing is, let's say this is a road. So let's say this is the plane of the road. This is the plane on which the motorcycle is moving. Okay, no? You have to see the figure. It's quite slow then. See, this cycle is moving, no? So this surface, let's say this plane, no? I've drawn a plane, right? So this plane is horizontal. So when he is taking the turn also at this path, again the horizontal force only will be the force will always be towards the center, but it is again the horizontal force only. I erased something. Did you see that? You can see, no. So see this this cycle is in going in a path, no. Let's say it is getting a turn now. So when it is taking a turn, there will be a force acting towards the center. Okay, but this force is still horizontal one, on this plane it's right, no. So all these forces are horizontal force only. The thing is, when the cycle is moving on with a constant speed, with centripetal force only it will be. So now the thing is, we know for this is a uniform circular motion. Okay, because there is no change in speed. They have not told about any change in speed. Okay, so now so what we have to do is the total force acting on the body is equals to mass into acceleration. This acceleration will be the centripetal acceleration. So mass into the acceleration is v square by the radius r. Fine. So what we have to find is the total acceleration, horizontal force acting on the scooter. What is the horizontal force acting scooter is needed to make the turn possible? What happens is, let's say we draw a free body diagram. So in this cases, what we will draw is, you will always imagine a circle around the free body diagram. Okay, no, understood. See, this circle is horizontally. I have to draw actually. So you have to understand this is a horizontal surface. Okay, so there is a force acting mg downwards. There is a normal contact force acting upwards. Okay, and there will be a, yeah, those will be cancelled. Okay, not an issue. So this there will be a horizontal force required towards the center. Okay, so this is the force what they are asking about. Understood, no? And this is the force. So this is see, you have to understand very carefully. This is 90 degrees to the surface of the road. This is also 90 degrees to the surface of the road. Understood? Imagine that the cycle is standing here. Okay, so this is the normal contact force and this is the mg. The tangential force will be here somewhere, and this will be 90 to both. This will be 90 to this also, and this will be 90 to this also, to this surface also. Understood? So we are not worried about this tangential force now. So we'll see that later. Okay, so this is a horizontal surface. So this circle is on a horizontal plane. So let's say you are taking a paper sheet. On paper sheet there is a bicycle or the scooter standing, and the mass mg is downwards, piercing into the paper sheet downwards, and the normal contact force is upwards, vertically upwards, perpendicular to horizontal sheet, and the centripetal force will be a line drawn on the paper sheet. No, I'm not drawing anything. You are understanding, no? So this will be a kind of a 3D. So you have to understand that. So this is the force required here. So this force will be equals to mass into acceleration. So acceleration, we know that this is equals to mv square by r. V square by r is the acceleration. So what is the force required here? Yeah, so omega square r, we won't use that because we are dealing here with velocity now. So when it is given okay, yeah, so 150 into 36 into 5 by 18 square divided by the r, 30 meters is the rate, 100 by 30, 150 into 100 by 30. So this is 500 newtons of force is required for the scooter to move in a circle. One thing is this, whenever we will be talking about theta, and whenever we will be talking about omega, so the unit omega. Okay, so omega. So whenever we are talking about theta, this will be given to you in radians. Radians are the angles. The theta is the angular distance, no? So this will be given in radians. Radians means angle, no? Degrees and radians. And omega will be given in radian per second. Right? No, so like the s was given in meters, so v was given in meter per second. So similarly, acceleration, this will be given in radians per second square. Okay, so here the acceleration was given in meter per second square. No, yeah, the speed will be varying in case of above, but we are not concerned about that now. This is just asking at the lowest. Okay, see what happens is this bob. Let's say it goes from here to here. Okay, so here the velocity will be zero. It will stop here, right? And it will be increasing. Here the velocity will be maximum, right? No, so you will understand this in simple harmonic mode. Okay, so the velocity will be there, but the thing is, we assume that, let's say this is moving in a small circle. Okay, so this is a part of a small circle. Let's say if we assume that this is a part of a small circle and the velocity at this particular point is given 1.4 meters per second. So this is part of a small circle. Let's say this is part of a I mean this is an arc of a circle. So let's say this is a part of a circle actually. So this length of the string will be this, the radius, right? Okay, so if we assume that this was moving in a circular motion, this was a part of a circular motion. Okay, so and the velocity, at this particular point the velocity is there. This is already given, so can you not find the tension? So what is the central force acting here? The centric, there is a force, no? This is attached by a string. So this is the tension only, no? So tension is giving you the centripetal force. Tension is actually giving the centripetal force. So this is the centripetal force. Fine. So tension will be equals to mass into centripetal acceleration. That centripetal acceleration will be equals to. Fine. So we'll move on to the next question. You understood? No, these are simple questions I am taking just for you to understand how the questions will be coming in the circular mode. Suppose the bob in the previous question has a speed of 1.4 meter per second and the string makes an angle of 0.2 with the vertical. Okay, so what they are saying is, let's say the bob is actually right now here. This is very small. Okay, I have drawn the diagram for convenience. So this is 0.2 radians is very small. So let's say the bob is actually here, and then at that particular point the speed is 1.4 meters per second. Find the tension at this instant. Can you find the tension at this instance? Now, okay, we'll come back to the previous question. One thing we have missed here. Okay, so see, this was the bob, no? So what we need to do is they are asking the tension in the string. So we know that this is the circular motion it is going. So there has to be a there has to be a centripetal force. That is tension here. There is a tension. There is a force tension acting towards the center, and there is a mass mg acting towards the other side also. Okay, so actually in this question, tension is providing you the centripetal acceleration, but the thing is mg is actually making it less. That will be equals to mv square by r. So you have to make it like. Now go to the next question. Now here also it is the same. Again it is same. So the thing is, what you have to do is you have to again draw a free body diagram. Let's say like this. So this is your tension acting here. Your mg will be here. So this is the tangential part. So if you see the angle, so this was angle 0.2. So this was angle 0.2. T. No, we have to see always towards the center here. You have to understand all the forces you have to take towards the center. T is there. T minus mg cos theta. So now the thing is, this way you have to solve it. You understood, no? What you have to do? Earlier what we used to do is in a incline or whatever, what we used to always do is we used to take all those forces in this direction, in the direction of motion, and the other one in the particular direction. We used to cancel this and used to take all the forces in the direction of the motion, direction of the acceleration basically. So here the acceleration is towards the center. The same thing we are doing here also. We are taking all the forces in this direction towards the center. So the center is towards the acceleration is towards the center. So all the forces towards the center is t minus mg cos theta is equals to mv square by r. All right, so t will be equals to t minus mg. What they have told is you can use cos theta is equals to directly 1 minus theta square by is equals to m into v square. V square is what? 1.4 square divided by r. R is your given in the first question. R is 1 meters, right? So you can solve it accordingly. This is 100 grams, so you have to take it 0.1 kgs. Okay, this is 0.1 kgs. So if you solve it accordingly, this will come. I just want to mention you one thing. This one is actually coming from this part. See, for very small theta, no, let's say sine 0 equals to 0, no, so this value and this value is equal, right? So if you take sine 0.001 degrees, this will come approximately 0.001 only, the value. So once you keep on increasing the value of sine, the theta, the value of sine also keeps on increasing, right? The graph is like this, no? Up to 90 degrees it will increase, no? Okay, so up to 90 degrees will increase from 0 to 1, it will increase, no? Okay, so now the thing is, it will increase. This is 90 degrees. This is origin. Okay, so this is going to increase. So for very small thetas, no, you can assume that sine theta is equivalent to theta. So what they have done is, if you see, so cos square theta is equals to 1 minus sine square theta to 1 minus theta square. So cos theta is equals to 1 minus theta square root. Okay, leave it anyways. You need not worry about those. We don't require here sine theta, right? All right. So the same question, but they are asking that if the bob is at the extreme position. Okay. So at the extreme position, what will be that instantaneous that velocity at that time? 0, no? So how you are going to find the tension at that point? So let's say this is your extreme position. So this is the tension acting and this is the mg acting. So let's say this makes an angle theta with the vertical, and that is the extreme position. Yeah, but there will be no velocity, no? So v is equals to 0 at that instant. So what you are going to do is t minus mg, this is theta, no? T minus mg cos theta is equals to mv square by r, that is equals to 0. So t is equals to mg cos theta. So mv square by r doesn't come here because there is no velocity. Yeah, the centripetal acceleration is 0 at that particular instant. As soon as the bomb again starts moving, the acceleration will come again in the picture. No, t is equals to mg cos theta. Mass will always be there. No, the mg cos theta will always be. This is 0. This is 0. V is 0. No, V is 0. Yeah, that centripetal acceleration is 0. This is 0. Okay, no. So the acceleration towards the center is 0. Understood? So since there is no motion, no, so this is circular motion, part of a circular motion, but here it is at rest. The velocity is 0 actually. So that time there is no acceleration towards the center. The tension is acting because of the mass. No, the mass is trying to pull it down. That's why there is a tension. That's right. That's right. So the tension is equals to actually the component of the mg force. Understood? No. That's why there is a tension. So this is the way you will be getting the questions. Okay, in the circular motion. Now there will be some complicated questions also.